sign in. You're passing it around. Yeah. Okay. Good. All right. Let's get started. Today is it the 17th today? 17th. And so what I'm planning to do today is, first of all, I wanted to ask you something about your project, right? Have you started the project at least now? Yes, now more people started it. Always is the last 2 weeks. Always this happens. Although the project will take you 3 weeks, but it doesn't really matter now. Now the damage is done. I'm joking. Of course, it will take you 2 weeks because the deadline is May 3rd, right? May 3rd. So it's like actually a little bit more than 2 weeks because it's a Sunday. And then when is your final exam? May 8th. Okay. Is this room? The final exam is in this room. Just make sure a couple of things I want to remind, and I'll be reminding every lecturer until the final exam. If you have accommodations, open a ticket. If you are, if you have accommodation, open a ticket, and we will respond to the ticket. I think Moses Center is it somewhere in this building? Moses Center, I think so, somewhere in this building. And as we did in the meter, the TAs will be here. I'll be on the phone, and I will present the exam. And the preparation for the exam I showed you last time, right? There are prep problems on the website. Did you see the prep problems? Yes. Okay. Yes. Go ahead.
Is it possible for you to be here during the exam?
Most likely no, because I have 2 residencies. So that weekend is Boston kind of weekend. If I am here, of course. But why are you saying that you're not satisfied with the?
Yeah, I think it would be like this would be better if you're like here. Like, sometimes it's better to ask you questions directly than this person.
Yeah, well, of course we'll consider that, but the TAs know the kind of more or less the type of answers. I think in the midterm, this was more of a time issue, I think. Like the midterm was required a little bit more of a lengthy kind of answers, and that was many people kind of ran out of time. You saw the statistics weren't really that bad, statistics of the midterm. So expect, I'm watching the statistics of the class, right? So I'm not going to be typically what I want is I want to get a nice kind of Gaussian distribution around something so I can assign my letters, right? And without shifting too much the threshold. So that's how the letters get to be defined, right? So if, for example, let's assume that in the worst case scenario, there's a difficult problem in the final and no one is able to solve it, right? Then obviously that's not a catastrophic event because the threshold will shift for everyone in the right direction so you can still get your reasonably good letter grades. I think historically we've been assigning good letter grades. I think people, despite the fact they were expecting the worst, they finally got out of this class with good letter grades. Of course, we cannot do miracles here. Okay, so last week we have finished the NLP. I told you we cannot stay in the NLP for much longer than we did because this week I have to finish logical reasoning and classical planning, which will take the form of, especially the classical planning will take the form of just introducing PDDL. And then I will do exactly the same thing. I'll give you some pointers as to how you can potentially enhance your understanding about classical planning, if this is what the area that you want to specialize on with certain kind of pointers which I'll point. Because the next 2 weeks are going to be probably the most challenging weeks of the course. Okay? Like the last 2 weeks is always challenging for 2 reasons. One is that everything kind of piles up. You have the project now to deliver. Secondly, you have to really spend time on Markov decision process and reinforcement learning. Who has here MDP RL education before? No one. Okay. Well, yeah.
She said MDP.
Markov decision process.
Yeah.
Yeah. Okay. So in these 2 last installments of this kind of lecture series, there will be many new definitions, and it's a highly mathematical oriented kind of discussion. So we need to get, I mean, definitely there will be some problem out of these last two lectures in the final exam. So I want you to be able to answer this type of questions, and probably you saw some of these type of problems in the prep final exam section. So at the end of this lecture series, you understand why they are there. So most likely there will be also some, I don't think I have the recursive state estimation in the midterm. Did I have recursive state estimation in the midterm or not? No one remembers. Anyway, I don't even remember, but I don't think I had. So there will be one problem on recursive state estimation. There should be one problem from before within the scope of the midterm to balance a little bit the exam. One problem on recursive state estimation, one MDP problem / reinforcement learning. And definitely a fourth problem will be on somewhat around architectures, right? Okay. So I kind of gave you a little bit some kind of more focus as a reward for those who came here today, and also those who, of course, will listen to the recording, which they didn't came. Okay. All right. So let's see. We entered the logical reasoning. I'm not going to do any grand review for the interest of time. And we kind of suggested that logical reasoning is going to build this kind of a new representation. We call it symbolic representation. This symbolic representation is going to be at this moment in time, and for this course, propositional symbols. What are the propositional symbols? They evaluate to either true or false. Okay, that is the definition. And of course, we have the typical operators that you probably must have done or must have come across earlier from discrete math kind of classes. And we will learn today how to work with a knowledge base. It's a database that is storing these sentences, also known as rules. And we are going to do inference. That's the conclusion of the logical reasoning lecture today, to do inference using two methods. One is the so-called model checking method, which is a kind of a fairly intuitive method. And the second method is a little bit more, I would call it difficult. It has to do with syntax. So we will be using some kind of lookup tables to find equivalences and prove via what's called a theorem proving the sentence that is true. Okay. So I will be using throughout an environment which is called the Wumpus world, which I think I introduced. No, I have not. Did I introduce Wumpus world last time? No. Okay, so I will start with that. But the bottom line is that we are going to be just using a simple game of some sort to do all that and conclude this kind of discussion. So today is the 17th. This is lecture 11. Or let me just draw something over here. This is the type subject is logical reasoning continue. So I'm going to draw over here a 4x4 world. We call this grid words also in MDP and reinforcement learning because I usually use this kind of small words to understand what's really happening. And in this world, which is there is a game going on. So let me put some coordinates: 1, 2, 3, 4. 1, 2, 3, 4. There is an unfortunate entity here called the Wumpus, a monster of some sort. And there is an agent that always starts from 1,1. And the agent is going to move in this environment, which I'll tell you a little bit about. And the aim of this kind of agent is to retrieve the gold, which is one of the cells, and which is right there in the 2,3 coordinate. Unfortunately, this agent is very conservative, and in order for it to move, it has to clear the cell next to it. Okay? It cannot move diagonally, it has to move in sort of vertically, horizontally space. Okay? And there is also unfortunate things like the presence of a pit here, over here, and over here. If you fall into a pit, you die. If you the pit around it creates some form of wind called breeze. So the breeze is something that the agent is able to perceive. So the agent has perception kind of capability. I'll tell you what this S stands for. Sense, and the agent is apparently smelly. So it's kind of meets that kind of sense perception. And then obviously when the agent moves here, so the extension of the agent, the monster must be somewhere around here. Okay? I do not know where it is, but the same thing happens here. When it moves in, there is a breeze, well, the pit is going to be somewhere around. Have you seen this example in discrete math or previously? No? Okay. It's a new example. So the agent also has. So what we're going to do to sort of determine an optimal way that we're going to retrieve the goal, win the game, so to speak, without getting killed, is we're going to assume a knowledge base. And we will populate the knowledge base with the rules of the world, which is before even the game starts. Like every game has obviously rules before it starts. And so we will just go ahead and populate them. I'm going to denote these sentences or rules with capital R letters. And I'm going to start with sentence 1, R1. Who can translate this sentence for me? There is no pit in 1-1 because the agent starts from 1-1. Effectively, this rule says, the game does not end the moment it starts. Okay. There's no humbus in 1-1 is another word, another sentence. Let me call this R0. What to mention? What about the presence of pits? I told you that, for example, R2, there will be P11, double implication, P12, or P21. So look at this rule now. Look at this rule. To tell me, what should I write in the right-hand side of this? So rule 2, I hope everyone understands that if there is a breeze in 1-1, right? Then there is either a pit in 1-2 or pit in 2-1 nearby. If there's a breeze in 2-1, what should I write here? Right. Obviously, if it's a breeze in 2-1, then there's a pit either here or here or here. Yes.
Could there be a breeze in 4-3?
Yes, there is indeed a breeze in 4-3. Thank you. So this is P11 or P22 or P. I would like to stress one thing. These are propositional symbols, and these are not the only sentences at this moment in time exist in knowledge base from the beginning of the world, beginning of the game. I did not write everything down. For every single kind of location, I can insert sentences. I just wrote some of them, which are kind of critical for me to get started. Yes.
But what's not W11? What's W?
W is this monster called Wumbus. That's why the game is called the Wumbus War. So what I'm going to do is we are going to do the following. I am going to create a table now of sequences of actions that the agent will be able to do. And we will use our own brain, first of all, to make logical inferences as to whether we can clear a cell and move on to the cell. And then later on, we will do exactly what the machine will be able to do. Okay? All right, so I'm going to start with this table. I'm going to write it over here. So the first column is state. The second column is percept. The third column is inference. And the fourth column is action. Step number one. I am in location 1, 1. And also I'm defining another propositional symbol, which is the theta east. I'm facing east, in other words. So both of them are true. And I am getting the following perception information. Okay, I'm getting effectively, I'm getting a whole bunch of nothing. Despite the fact that in reality, getting nothing for us means, okay, there's nothing there in the X vector that we did kind of earlier. Over here, we are actually storing everything, even in the absence of perception information, in the knowledge base. There's no breeze, there is no stance, for example. A whole bunch of rules will be there. I'm just writing only again the ones which will allow me to highlight logical inference. So I'm going to put a dot. Okay, inference with our own brain. If there is no breeze in 1, 1, right? No. Okay. If there is no breeze in 1, 1, what can we infer? That there is no pit, right, in 2, 1, right? Or there's no pit in 1, 2. Let me write down the R6, which is there's no pit in 2, 1. And therefore, I can go. And now I'm going to be occupying what? Location 2, 1. In that location, however, I'm getting the rule R5, which is B21. Getting this percept. Therefore, I am concluding R7 that there is P31 or P22. Do you agree? Also, I'm concluding something else. I'm concluding that there is no Wumbus into 2 and no Wumbus in 3-1. I hope you can read it, especially at the end. Try to compress it. This is 3-1. Why I'm concluding all this? Because obviously I don't have a stance here over here. So I'm using my own brain to just understand what's really happening, what the logical reasoning rules that are going to be stored in the knowledge base from the computer later on. Then finally I say, okay, fine. I cannot clear this cell. I cannot clear it. So what I'm going to do? I will turn back. I'll go back. Again, I'm conservative. Right? I am going to, I cannot go up here because I just concluded that there may be a pit over here. I cannot clear either of these two cells. So I'm going to go back over here. And I am going to suggest that I'm skipping, I'm going to write number 3 very, I'm facing now west because I went back, so I skipped some things. I'm going to turn. And I'm going to be facing now north. Okay. In north, I am going to suggest that since I'm here and I didn't get any breeze, this cell is cleared. Okay, there's no pit, there's no humus here that didn't get any stents here. This cell is cleared, no? Just like this cell was cleared, right? So this cell is cleared. So I'm moving now into, I'm actually executing, I'm inferring that there is no pit in 1, 2, and I'm going forward. In later, I'm reaching now L1, 2 is equal to true, and I'm facing north, and I'm getting a percept. What should I write here? In location 1, 2, what should I write here as percept? S12. S12. I am now inferring that W13 is true. Do you see why I'm inferring this? Okay. Why? Why I'm inferring that W13? I'm getting a stance right here. Why I'm inferring that the humus could be, of course, either here or here, but now I'm inferring that can only be here. Why? Yes? Because obviously, if the humus were here, I would have sensed the stance over here, and I didn't. Okay. It's kind of a simple thing if you think about it. It's just like a toy sort of game, but it's kind of useful to. So what we are effectively understand now, first of all, there is no pit in P22 that we knew. There's no pit in 22. Yes, there's no pit in 22. We didn't know it. We just learned it. There's no pit in 22 because we're suspecting here there is a pit either here or here. We couldn't go there, therefore we went back. We went this way. The moment we arrived there, because we don't have breeze, we infer that there's no pit to 2 here, okay, in this location. Therefore, we are going to turn because we don't want to go up and die. So we're going to turn and we are going to arrive at L22 is equal to true, facing east. Now, I can continue. The long story short is that if I go face east over here, I will get stuck again. And therefore, I will have come back into L22, so I skipped like one line. And of course, the only thing that I can clear is what? Is this cell. So I am going to turn to face north. L23 is equal to true now, facing north. I am sensing S23, B23, not W, but gold, and I am inferring that there is gold here, and I'm issuing the action grab, and then the game terminates successfully. This is basically a kind of a 5-10 minute kind of summary of some interaction with that kind of environment. And now what we are going to do, we are going to start listing some interactions with the knowledge base that will be helpful for us to mechanize this. So I'm going to start titling this kind of discussion, knowledge-based interaction. Just like in ordinary database, we have two operations, read and write. So first of all, what is a knowledge base? Just as a definition, a set of sentences that represent rules of the world, model, percepts, and inferences over time. The knowledge base will expand, will contain more and more sentences. I want you to start thinking this fact as increasing the number of constraints that I have. I want you to start thinking about an additional sentence as an additional constraint in optimization theory kind of way, okay? In a sense that it will become increasingly difficult to satisfy the knowledge base the more rules are being added into it, which is kind of intuitive, but it's good to think about it this way. So we'll use some Venn diagrams to visualize and understand the KB operations. And there will be two operations which I will define, the so-called ask operation and the so-called tell operation, which is kind of resembles the read and write operations from the ordinary kind of knowledge base that you're familiar with. So there are two operations as I just mentioned. The first one is a tell, and alpha is a sentence that I want to inform the knowledge base so that I can ask it to store it. But the knowledge base, contrary to the ordinary kind of knowledge base, the knowledge base contrary to the ordinary database, it will be able to answer in three ways. I knew that. Something that we call an entailment. The second answer that we receive is, I don't believe that. Something that we will call a contradiction. And the third is update. AB, something we'll call contingency. And in this case, the new sentence becomes part of the knowledge base. Okay. These are the three things that can happen from the tell operation. There are three things that can also happen in an ask operation. The knowledge base will either respond as true, false, or I don't know. So we're asking something about the sentence. Is a sentence true, false, or I don't know? That's basically what the knowledge base will respond. We want to write something in the knowledge base. The knowledge base will not do it, either because it already knows about that sentence, or there's a contradiction that it isn't there that prohibits for the right process to sort of have two states for the same sentence. Or if it doesn't really know anything about the sentence, new information, if you like, we'll see some examples in a moment, then it will update the knowledge base and add this kind of sentence. So I'm going to start this kind of discussion with these tell operations, and so they can understand these responses. Operations. So the first operation is so-called is I knew that. And this is, we call it as entailment. And there is a special symbol that we symbolize in logic the fact that have a sentence before on the left-hand side, the right-hand side of this kind of entailment symbol. I'll give you an example. And I'll also draw a kind of event kind of diagram. So let's assume that I have the knowledge base right now. So this is basically an example. I have the knowledge base right now with inside the knowledge base there are two sentences, A1 and A2. So if this is, remember from the earlier discussion, the set of models that satisfy first sentence, let's assume that this is the set of models that satisfy sentence alpha 1. Okay. Now, you remember the example of the set of models, the capital M that I wrote in the previous lecture. For those who forgot, this is the set of models that satisfy this sentence, right? This is the set of models that satisfy this sentence for these two propositional symbols. So we use the Venn diagrams to just graphically see what is happening, right? Let's assume that all these models are in this circle that I drew, as far as alpha 1 is concerned, the sentence alpha 1. Okay, and let's assume that there's another set of models that satisfy alpha 2, potentially different. Okay. Now, if there is an intersection between the two, right? This intersection is, I'll write it here, is the set of models that satisfy the knowledge base. So if now a new sentence comes in and I want to exercise the tell operation for that new sentence, I'll call that new sentence alpha 3. In other words, I want you to store alpha 3 into the knowledge base. So I'm writing here, tell. When is the case, what in terms of the Venn diagram, now I'm going to draw the case where the knowledge base is, I already know that. I'm not going to update the knowledge base because I already know them. So here's what is happening. M A3 is a set of models. The set of models that satisfy the sentence A3 is this exterior. And this is a set of models that satisfy the knowledge base. If, so I'm writing now, if the set of models of A3 intersection, set of models of the knowledge base is equal to the set of models of the knowledge base. In other words, the presence of A3 did not change the set of models to satisfy the knowledge base. A3 is not a new information. Yes.
Knowledge base can be bigger than alpha 3, right? So M of alpha 3 intersect M of knowledge base shouldn't be like the smaller of the two. Like M of alpha.
We'll come to that. I mean, we'll come to the other case where, in fact, there is a new information. And that is the case over there. But in this case, right, where the intersection leaves the set of models that satisfy the knowledge base unchanged, that is where the intuition is. Leaves the set of models that satisfy the knowledge base unchanged means that the alpha 3 does not offer new information. Yes.
Can we not just say M of alpha 3 is a subset of knowledge base? Then entailment is agreed.
So in this case, M of alpha 3, right, is a set of models. If there is no change in this, then we have entailment. If there is no change from the shaded portion that I drew, we have entailment. In other words, what alpha 3 brought in the table was already known in the set of sentences that already was there. Now, let me write it down. So then the response will be, I know that, and we'll write knowledge base entails alpha 3. Let's now move on to the easiest kind of case. The easiest case is contradiction. If this is be careful, sometimes I draw the big circle. This is now the set of models that satisfy the knowledge base. I will write it down. M, A, B. And there's no shading, in other words, here in this specific case. Okay, it's kind of there's no consistency, in other words, between the cases. And then there's M alpha 3. In other words, we have no common ground. On between A, B, and the new sentence. Then the knowledge base will respond, I don't agree with that. Now, the third one is what we call the contingency. And now we have the set of models that satisfy the knowledge base intersecting with the set of models that satisfy alpha 3. And if then the alpha 3 being part of the knowledge base now means that the set of models that satisfy the new knowledge base, the updated knowledge base, is where? So if this was a set of models that satisfy the knowledge base, and alpha 3 comes along, and alpha 3 is new information, right? The intersection. So the set of models that satisfy the knowledge base after the addition of alpha 3 is going to be this guy over here. Mind you, the shading means different things in the different conditions. So I can write that M of knowledge base intersection M A3 is a subset of M knowledge base. And also, I can also write that this subset is non-trivial. It's a non-trivial subset. So in other words, I can write that alpha 3 reduced the set of models that satisfy the knowledge base. And what it knows does not contradict alpha 3, then we have the contingency. So we have the knowledge base will be updated. We include now, let's say 3 sentences, the alpha 3 sentence, whatever the previous content is, and the alpha. Yes.
Here it has to be a strict subset. If it is equal, then it's not a contingency, right? So if M of KB intersect M of alpha 3 is equal to M of KB, then you're not adding new information. That's why you're having a strict subset.
Yeah. We'll see now an example now on this. When I look at the Wumbus wall, I go back to the Wumbus wall and just show you some examples of that in a moment. Now, what I want to do now is just briefly go over the ask operations, which is kind of now going to be based on this kind of entailment discussion we just had, the number one discussion. So if I write here the ask operation, so I am, as I told you, I'm going to send a query to the knowledge base, and it may respond to true. Now, if the knowledge base can do number one, in other words, can entail, already knows about this sentence, it will respond with true. If it can entail the negation of the sentence, will respond with false. And it will respond with I don't know. If it cannot entail either the alpha or its negation. In other words, we'll see an example for that in a moment on the model checking, right? So I don't insist so much on that because the example now is these operations will be understood to some degree from the subsequent kind of discussion. And this subsequent discussion now has to go back to the Wumbus world and repeat what we did with our own brain, repeat it now with using the two approaches. The first one is the model checking approach. So I'm going to title this discussion the logical reasoning with model checking. And I want you to go back to this table that you wrote, where at some point I am going to issue now the ask operation again. We just covered that. Ask about what? Negation of P12. There's no fit in 1, 2. I'm going to ask you about this, the knowledge base. And I am going to ask about this knowledge base because the knowledge base continuously being updated. I'm going to freeze in time the knowledge base, assuming that I'm in t is equal to 4. Okay, so I'm going to write this down because it's important. Ask about P, not P, but P, that is P12 operation issued when knowledge base is at t is equal to 4. So we'll go back to the, so I'm writing that at t is equal to 4, okay, we will assume, this is an assumption. I'm not so sure if what I wrote is exactly strictly speaking or there is an additional kind of rule, but at least in my notes, in the knowledge base, I'm going to have a set of rules. Okay? I'm going to fix the set of rules that I have in the knowledge base to pretend that this is basically t is equal to 4. And these rules are R1 to R5, I'm saying here. Let's go back and check. R1 to R5. Yeah, let's assume that. I will assume we'll fix the set of rules. Okay. So we assume that only rules R1, R5 are in the knowledge base. So we'll go to these rules and say, okay, there's rule number 1. What propositional symbols does this rule number 1 includes? Okay, so I'm going to write down that the symbols in these 5 rules include P11, B11, B21, P12, P21, P22, P31. 7 symbols are involved in these rules. With some operators among them, that doesn't mean. So 7 symbols total. And I'm going to enumerate all models, small letter m, according to the previous terminology we had, I, from I obviously I have propositional symbols, each symbol is binary, so I have 2 to the power of 7 possible models. What is a model? Small letter m, an assignment of true or false for each of these symbols. So we are going to create a table. I'm not going to create a table, obviously, with 128 rows here. I'm going to just read it from the website. Hopefully I have it here. Nothing catastrophic happened. So I am going to take these symbols 1, 2, 3, 4, 5, 6, 7, right? I'm going to have the 7 symbols. For each row corresponds to an assignment from 0, 0, 0 all the way to 1, 1, 1. And then I'm going to have the corresponding 5 rules that I have in the knowledge base. And I told you when, last time, I think I told you when the knowledge base is satisfied, when there is conjunction of all the rules present in the knowledge base evaluate to true. So I am going to take this assignment, look at rule number 1, and write down the truth value of this specific rule. As an example, I want you to think about the evaluation of R2, the second rule, R2 that I have in the knowledge base, B11, double implication, P12, or P21. So I'm picking up a row out of this 128 sort of rows, right? I'm picking up a row where P12 is false, P21 is also false. So I'm evaluating this guy. So we can write, in other words, that P12 or P21 is false. I hope you agree. In this specific row, B11 is also false. In fact, it is really the first row, as it turns out. Come on. So what symbols they have? I forget. P12 and P21, I think, right? They're all false. B11 is also false for this specific model. So I'm having the rule now looks like this. False, double implication false. What is this? What is this rule evaluation? I'm going to the truth table of the double implication. The truth table of the double implication. And I think I did it last time, right? So this evaluates to true. Okay, first row of this table. Okay. So this evaluates to true. So in other words, R2 is true. For this specific model, R2 is going to be true. For some other model, R2 may be false, okay? Which means that I need to go and do that for all my rules. And as I can see here, if there is one false in any row over here, this thing will be false, obviously. So there are lots of falses, but a small subset of models make the knowledge base satisfied. Okay, so this is true. And I'm saying the following now. For this specific set of models, what is the value of the sentence that I'm interested in, right? What is the value of the sentence I'm interested in? Okay, so P12 is false in this set of models. P12 is false. It's false across the set of models that satisfy the knowledge base. Therefore, the negation of P12, which I asked the knowledge base about, will evaluate to true. If this is true to true, but in what was the symbol again? P12, I asked. If one of them was true over here and the rest was false, what would be the situation there? What would be the knowledge base response? I don't know. Because I have conflicting information about this specific sentence. I do not know. So I'm writing out of 128 models, only 3 satisfy the knowledge base. In these 3, P12 is false, which means that the negation P12 is true. Okay. And this is basically the end of the model checking discussion. An exhaustive assignment followed by checking each model as to what the satisfy is happy about, evaluates to true, and then going back and evaluating this rule. And if it is a consistency, we can answer either true or false. And if there is an inconsistency, we can answer I do not know. Which brings us to the second discussion, which is theorem proving, which uses only syntactical rules to prove something. Okay, so we'll use again another example to understand how this thing will work. So now the discussion is logical reasoning with propositional theorem proving. So in logic, so basically, if you remember, this discussion is entirely based on syntax alone. We're not really doing any modeling or anything like that. We don't do assignments. We just look at the syntax. No matter what the assignment of every symbol is, we only use syntax to come up from use and some kind of additional kind of inference rules to prove the sentence. Okay, so I am going to introduce two inference rules that we're going to use. The first one is called modus ponens. And I'm going to write it as a fraction over here where the numerator will be the premise and the denominator will be the conclusion. And if alpha implies beta, and I know that alpha, then I can conclude beta. That's the modus ponens. And the second is called the end elimination. Again, the same kind of format, premise, conclusion, alpha and beta, alpha. And it's exactly the reverse is also true. Beta and alpha, beta. So I'm going to use a sentence that I used in the throughout the kind of the game that I sort of did with the Wumbus wall. And the problem is the following. This is basically the example. So that P12 and P21 is equal to 2. Now, these are not the only things that I need to use. I need to use also a lookup table, which you have to have a printout. Well, you don't have to print out. If there is a logical reasoning question, I am going to include it in the set of questions that I'm going to give you in the question itself. So this is the, unfortunately, I don't have it in the website. Let's see. If you Google, however, 7-Eleven from the book, not the store, but the 7-Eleven table, right? This is the table. This is a lookup table of logical equivalences. So you see the equivalence kind of symbol. You can swap this guy with this guy, this guy with this guy. So by starting from some sentence that will accept as true, we will evolve into a sentence that we are after, that obviously it will evaluate as true because they are equivalent. And we are using just syntax to write one sentence after another. So I am going to leave this up, but if you have computers, you can bring it up also, as well. It will help the discussion. I'm going to start. I'm going to start with the following. So start from a rule R2. I had the rule R2 in the Wumbus world, which is P11, double implication, P12, or P21. Now the question is, okay, where is the magic here? You just started randomly from some rule. Well, okay, there's no randomness, of course. Here, I mean, I looked at my propositional symbols involved in the sentence. And out of the rules that I accepted to be the knowledge base, they are in the knowledge base and evaluates true, I picked up a rule that involves these two symbols. And with that, I will write in the 7-11 kind of table, I will make the next step. So initially, the next step is kind of evident. I will replace the double implication with the conjunction of either of the two implication rules that we know without really looking at the table. So I am going to, in fact, there is a table, there is an entry. I mean, it's called, sometimes the names are like, okay, by conditional elimination. Okay. By conditional elimination, you can see the row over here, and I'm just going to apply this rule. This equivalence. So I'm writing B11 implies P12 or P21 and P12 or P21 implies B11. This is, I'm going to call this R8, and I will explain elimination. Now, remember the inference rule? Which rule of the two you think you will apply now? Which of the two rules that you see here as inference rules would you apply? Yes.
Second one.
Second, and elimination. So I'm writing now, in other words, that P12 or P21 implies B11. And this rule, I will call it R9 and elimination. Okay, so this step is not intuitive, okay? I'm just going to write it. I'm going to apply the equivalence of contraposition. Well, it's kind of intuitive in a sense that at the end of the day, I'm looking at this here and I see lots of negations around, right? So I kind of sense that I'm going to be looking at this 7-11 table. Do you see the contraposition? So alpha implies beta, negative beta implies negative alpha. Okay. So I'm going to write it. Whatever. Negative B11, negative P12 or P21. Be careful. Okay, so this is the R10 contraposition. Finally, I can combine. I will apply modus ponens by combining R4 and R10. So if I combine R4 and R10, which is basically this guy over here, and R4, let's look at R4. R4 is, unfortunately, R4. Let's see. Do you see any R4 here? Oh, this guy. Okay. I have this implies comma this is modus ponens 1 2 1 2 2 1. This is R11. And finally, the last line is now that I have reached over here, this is equivalent to negative P12 This is called the De Morgan rule. Which is R12, which is basically what I was after. I understand that the sequences are not sometimes intuitive, right? And require some kind of experience, right, into this. Now, your textbook has some examples, and as I told you again, for the final exam, 48 hours before the final exam, I will tell you, right, some topics. If you don't see logical reasoning there, you don't need to look into this. Okay? But I cannot say more. Any questions on this second part, second method? Pure syntax. Nothing of model checking. Obviously, it is itself a method which is obviously powered by domain-specific kind of software who is going to do this for us. But I cannot really expand too much into logic because we will not cover other things which are even more important. The only thing, as I told you last time, is that theorem proving has been shown to have good applications in AWS today, and also to some degree propositional logic and knowledge bases also have, in combination with the planning definition language, or PDDL, has also applied to some degree in robotics as well. But I'll leave it at this point, and I'm glad that we reached a point where we can move on to another topic. Okay, not my favorite topic, honestly, but it will not be the same, whatever. Okay, so I'm going to if I find this, I'm going to move on for the interest of time to what is called the automated planning. Now, automated planning is a huge, of course, domain. And just give you an example. Planning. So in the planning, obviously, many people, I mean, this is certain type of algorithms that are undergrads even undergrads must know something about. First search and all this kind of stuff. So I'm not really covering this, even as an overview. The topic that I will want to focus on is this called effectively task planning. Now, planning is like such a huge kind of discussion. If you go to a robotics class, you probably will do motion planning. There are also some other types of planning these days, like behavioral planning, where you are also considering in a multi-agent scenario the behavior of the other agents in your planning. And along these lines, there is lots of stuff in the, I would call it in that kind of domain. So over here we look at the task planning, where someone will actually give you a domain, someone will give you a problem statement, and will ask you to determine the optimal sequence of actions, let's say, to solve the problem. So there will be some kind of a domain, let's say logistics, whatever. There will be some kind of initial state, some kind of a final state. The domain will need to be expressed in a special language that will, just like in a programming language, you have types, classes, right? You have data classes, you have this, you have that, you expect, to give you an example, in last year, I think it was last year, I can't remember now, I gave out an assignment on PDDL as in the domain of Open Route. What is Open? You know Open Router? Yeah. Open Router is company who is routing LLM requests, right, to various kind of providers. So obviously, Open Router has a domain. It's a domain or it's a routing domain, right? So for that specific kind of high-level function, and obviously you need to have an automatic way to come up with the types inside the PDDL language, right? So what do you do to come up with types in a language? Like, for example, forget about PDDL, look at Python. How do you come up with a data model, in other words, right? The data classes, some of you might have be aware of. So you go to the website and you start mining the website, right, for information. Oh, there is a data class has to be an LLM provider. Another data class could be, I don't know, number of. I'm forgetting now, but if you go to the Open Router, there will be plenty of examples where people have defined this kind of data classes, and then of course states in this kind of problem will be okay. I have a request, and I want to optimally route it, subject to some kind of a cost constraints to satisfy that kind of request. Because maybe there's a max number of tokens that this request must consume, some constraints such as this, right? So you put that in the state. So over here we see a physical example where the state is associated with boxes and sort of tracks and things like that. And the optimal thing is, okay, if I want to load the boxes into the track, what is the sequence of actions that I need to perform? Trivial example, but it's sufficient for understanding where we are going. So let's try to see now. So in this PDDL language, we are going to work with two things. The domain model and the problem description. The domain model, as I said, will contain the classes, and the other problem description will contain the initial state and the goal state. Now, the domain language is effectively processed by what's called a planner. Now, these planning algorithms, right, are in the general kind of family of search kind of base schemes, for example, right? And we're not going to dissect these planning algorithms because, like many lectures, what we need to do, at the very least, is to familiarize ourselves with this PDDL and as a language, hit it with a planner, a general kind of planner for the specific problem we are interested in, and observe the actions. That's all we will do. Now, here in this kind of class, because of computing kind of requirements, I'm not going to be able to demonstrate this part, the actual execution part. However, if you go to my YouTube channel, you will be able to see in VS Code the planner being executed and the PDDL planning kind of files being consumed by the planner to. So there are some URLs where these planners are sitting there and waiting, and you hit them with PDDL requests, and they come back with this kind of functions. So our job here is kind of very constrained to understand the language, some elements of the language, not the complete kind of thing, and move on. Okay, so let's see. Over here, I'm going to write certain things. So I'm going to write, first of all, that we are going to be discussing about planning, domain, definition, language, PDDL. So we will dissect first the domain. As I told you, the discussion is very limited. So domain.ptdl file will contain, obviously, the things I explained, the types. In other words, the classes. Will contain predicates. We'll see an example in a moment. That was, of course, say something about the subject of a sentence. Will contain action schemas. And will contain also preconditions and effects. Okay, to give you an idea, take for example the blocks world. Okay, what happened here? Oh, now we see something. Okay, so the blocks word is so trivial that doesn't require explanation. I will expand now to the problems, to the problem, to the PDDL. And the problem to the PDDL will consist of the initial state and the goal state. Now, these two files will be there. Obviously, the domain is kind of the important component and probably the most difficult one to specify. So I'll spend some time on explaining what is really PDDL state and the concept of an action schema, because these are the most important parts. The types and classes, I think it's kind of intuitive. Okay, so I'm going to explain here the PDDL state. So it's a conjunction of ground, atomic, fluence. I'll explain. This is like formal definitions on this kind of language. Maybe I can explain it. Maybe explain it as an example. So let's assume that this is basically the state B, and this is the block A on top of C. This is called block words, block word kind of domain. So I'm writing now the state, which it will be like on A, comma table, and on, that's a predicate, B, comma table, and on C, comma A. So here we have specific objects out of the class block involved with the predicates and this kind of a conjunction to define, if you like, the PDDL state. An action schema. Go in the domain file. So this one is called schema because it's a family of ground actions. So let me use an example. An action schema will have the signature, so to speak, B, comma, X, comma, Y, and it will have a precondition. I'm writing like as I'm writing the language. If you install in VS Code the PDDL plugin, then the syntax will be straightforward for you to. I mean, it will do highlighting and things like that, and also will point some errors if you have. So the schema is called schema because it does not really specify the specific block, right? But specifies the type, right? So, for example, as a precondition to move the block B and on top of the other, let's say, the three things are involved here. There is a block. The B is a type block. The Y is a type block. Let's say X could be the table, right? As an example. So I'm going to write a precondition on B, comma X, and clear B, and block B, and block is the type Y, obviously, as you can see here, Y, and B is not coinciding with X, and B is not coinciding with Y, and X is not coinciding with Y. It is a precondition for me to execute the action. And the effect of this kind of action is also going to be present. And you can see that in some of the examples I have on the website on B, Y, and clear X, and on B, X, and not clear Y. Because now the block B is on top of the Y. So as an example, this schema can be applied as follows. You assign B to the block B, you assign X, let's say, to the table, and you assign Y to the block C.
Wait, Professor,
Yes.
we already said in the effect clear X, which means there's no block on top of X, right? But so we don't need to say not.
Yeah, I'm okay. The truth is that this is what I saw on the book. That's what I wrote. I have no idea if this is a double thing or not, or if it is needed. Honestly, I don't know. But yes, I mean, the predicate kind of clear, they imply this one. So I know what you're saying. Yeah. So this is basically some example of the kind of domain and problem statements that we'll see. Let's look at an example now. So block's word is actually here. Honestly, this is the only example I want you to at least look to understand what we just discussed here. Okay. So we have the sort of, this is also a classic planning problem. Now there is some brave person defined this unified planning library, a Python package. And this Python package effectively allows you to specify exactly the same things. In fact, you can go from PDDL, you can import PDDL files into that kind of package, and it will convert it to Python classes. And then everything is kind of in a very familiar ground if you do that. So there's a button over here, run the tutorial. I'm afraid that this tutorial will not run as it is. Maybe it will run, maybe it will not run. I have not really checked kind of recently, but let's be brave also and try to run it. Okay. No, it will not run because it has some dependencies. Definitely visualizations will not run. It will have some dependencies like this library that we cannot really get rid of ever, which is from Bell Labs called GraphViz, like from the 70s. And still remember some people working on it. That's how old I am. So there are some dependencies, and the notebook's not working. But if you take the notebook and download it, and you install these dependencies locally in your personal kind of computer, where GraphViz, it's a very usual dependency for visualizations of graphs. Then the steps will be sort of replicated, and the notebook will run locally. So this is basically one example, but if you look at the notebook, this notebook has now the unified planning kind of library, and so it will create a new type for you, right? It's called block. So this is basically what the clear means, the predicate clear on table R empty. Obviously, there's a robotic R with moving the blocks, holding and on. The guy who did a lot of work in NVIDIA is called Chris Paxton, and you can read some of his papers if you want to combine PDDL with probabilistic kind of robotics. So these are the things that unfortunately we're not able to cover. Then obviously we have the pickup action with the preconditions and the effects, and more actions, schemas, in other words. And then finally, at some point, we need to start looking at the problem. Okay, so in the problem, we have to instantiate the objects because we need to have specific blocks. We need to define, if you like, an goal state and initial kind of state. And finally press the run button. Nothing really. Then the solver will be involved, and the solution will be printed. As I said in my YouTube videos, I have worked on this in the desktop kind of environment, so your solution was there with nice graphics if you want to. There are some more complicated domains, like in logistics and in manufacturing, that I have included over here. But some of the problems are not really using the Python, but you can actually see the language is not a language that you can absorb it like in a day. It's like it's a language which these days probably an LLM will write for you. Okay. Now, having said that, and despite the fact that some of you may think, okay, why we learn about this? There was, oh, that's very unfortunate. I had the, so this behavior, there's a huge effort on coming up with synthetic data. If you watch the Howard Huang, right? He is the CEO of NVIDIA interview. Did you watch the interview? Was it 3 weeks ago, 2 weeks ago? He talked a lot about the value of synthetic data. And they are in a very fortunate kind of space also themselves because they are they have photorealistic capabilities, right? And so they are actually able to generate quite a lot of data by combining the robotic simulations that they have been working, like anyone knows about Omniverse? NVIDIA Omniverse? Okay, yeah, Omniverse. Obviously, there is an ISAC there, a simulator. So this behavior kind of project, it's also a competition, is very heavily attended by Stanford, NVIDIA, the usual kind of, and also from NYU actually as well. And they are creating, if you like, the action data sets for humanoids. So one of the things that they are actually doing inside what's called now Omni-Gibson, Omni-Gibson took the name from Omniverse, and the Gibson was the original kind of simulator, is called PDDL. Okay, if you open the PDDL, B stands for behavior DDL. So it's not planning; it's behavior of the robot, of the behavior we try to induce. Okay, so we have a domain, the kitchen, and we have, let's say, robots that are humanoids that are trying to execute some kind of tasks in this kind of kitchen domain, and then we use this domain-specific language to create some form of determinism, right? So, because obviously in this kind of projects, visual language models and visual language action models are involved, right? In other words, they are statistical machines, expansions to what we have done in this kind of course, but they also need to be coupled with some determinism, right? Otherwise, you cannot really bet that the statistical machine will do the right thing all the time. So they're using the planning-oriented kind of languages to plan this kind of actions. And some of these actions are mainly here are generating, if you like, the tasks, so they can actually do tuning of these language models, right? To tune the language models from these actions that the robot is supposed to take. So it's basically a sim to real environment, a sim to real, simulation to reality environment where they can transfer the policy they learn from the simulation to the real robot. So lots of stuff are happening. So it's not really The discussion here is like very superficial, but behind it there is some, just coincidentally, as I was looking at the latest kind of thing, I came across this, which is this project at MIT, who is also using PDDL. MIT has some tradition with this language, the planning definition language from the Tandem-Bounds kind of team, that they combine LLMs and PDDL. Not only for LLM to provide you with PDDL and therefore do planning, but here they're using it. I will include both of these links in your Discord. So because I kind of finished a little bit the logical reasoning and the planning kind of discussion, I would like to start what I was telling you earlier about Markov decision processes and reinforcement learning, and kind of start really slow on those ones. So we don't kind of start with some kind of basis on to the next lecture. Don't do that. Have you seen Indiana Jones movies? You remember Indiana Jones? You know Indiana Jones? It's like the guy who goes around to find sort of some treasure. And in all the movies, when he goes to find the treasure in the kind of, then there are a lot of skeletons around, right? There's a lot of skeletons. So I want you to remember this kind of analogy, because many people try to learn reinforcement learning and they end up being skeletons. In a sense that the path is kind of long and it's painful. So don't be discouraged immediately from the avalanche of definitions of equations, mainly specifically in this course where it is, we also have undergraduate students. So don't run for the door immediately. Just give it some time and believe that at the end of the day, there is a light. Okay? And it's not a train. It is a light of, a good light. So I want to tell you that because most of the treatment here is coming from two key textbooks. One is the Richard Sutton's book, which is really the Bible of reinforcement learning. And the other is from a lecture series that happened in Oxford several years ago by David Silver. So David Silver is the person who is behind the AlphaGo sort of thing. And so from that kind of perspective, the discussion is going to be mathematical. Okay? But as I said, you can see, I hope, in this kind of course, if you write down the equations and you spend some time on it, writing them, translating them in English, that's how you learn. Okay? And that's how you remember, by also making some analogies. This is the approach I'm going to do today and tomorrow and next week. So let's start. I'm going to start with Markov decision processes or MDP. Let's look at the example here. So the difference between the planning we just completed, of course, we didn't complete any planning, but at least the superficial discussion on planning a sequence of actions, is that that kind of planning does not involve any feedback signal from the environment. I'm moving a block from here to there. Whether I moved it correctly or not, no one is telling me about anything. Obviously, I will never reach the goal state, but that's the only thing that is going to happen. Over here, we're going to have planning with interactions. So we're going to have an agent who is interacting with this environment. just like the agent we have done all along in this kind of course. It will receive some perception information, will take some actions, and it will transfer from one state to another, a transition from one state to another, and at the same time receive a signal from the environment called the reward. It is really that signal that it is really the difference, and this signal will complicate things as well for us. We'll assume the usual setting of stochastic environments. So from that perspective, things are kind of understood. Stochastic environments, remember hidden Markov models and things like that we did. But also we'll assume that sometimes our actions are also not deterministic. Okay? So our actions will be often probabilistic. This is another complication. So probabilistic state transitions, familiar. The reward signal itself is our responsibility to design the reward. What exactly this reward is going to be done for the specific transition to states, for the specific actions that we do. So this is basically the block diagram. So from the perspective of definitions, I am going to write these things down gradually, but from the get-go, I hope everyone is familiar with the state. Evidently, state transitions, obviously we need to write T together with the state, ST, ST plus 1, ST plus 2, and things like that. We are going to also take actions over time. In fact, this is what we are after. We're after optimal set of actions to maximize something, maximize an objective. And R is going to be the sort of reward that we are going to be receiving. Okay. Capital T sometimes will be used either by indicating a terminating state or indicating the length of the episode. Okay, episode is time horizon from T to the termination, and sometimes I'll use also the trajectory to indicate that there is some kind of sequence of what we call experiences, this interaction with the environment. The rest is, you can forget it, we will define it right now. Okay, so let's start. So I'm going to define this transition we just saw as a block diagram, but I will unroll it. I'm going to start with some state, ST is equal to S. Now, in terms of terminology and notation, capital S will denote the random variable. In fact, capital letters will denote the random variable, and small letters will denote the specific value that this random variable is taking. Okay. And these values will actually have some primes on top or double primes. Prime will be translated to next. S prime is the next state. S double prime is the state after that. It's like that. Okay, so we are taking an action, and we are receiving a reward while at the same time transitioning to the next state. This is the responsibility of the agent to do that. This is the responsibility of the environment to do that, to transition us and to send us the reward. This is the okay, and this is the agent again. And so on and so on. So this interaction will continue. For small letter r, we will say the specific rewards, a scalar that we'll call reward. And obviously, you can understand that this experience will be a triplet of S, A, R, comma, S prime, A prime, R prime, comma, dot, dot, dot. This is what we call the experience. And a Markov decision process is going to be defined by this calligraphic M, by a 5-tuple, calligraphic S, calligraphic P. I will explain, of course, everything, calligraphic R, calligraphic A, and gamma. So this calligraphic S is going to be the set of states. Calligraphic P is going to capture the transition model. Calligraphic R is going to be the rewards and actions. And this guy is going to be the so-called discount factor. This 5-tuple is now set. We have defined the MDP. One key thing for the discussion we're going to have, over here we will know everything. We will know the transition model. We will know the reward functions that are needed for us, for the environment to send us a reward. We'll know the discount factor. So despite the stochasticity, some things will be known. In other words, probability distributions will be known. In order for me to start defining and write down probability distributions, because remember what we have done also in the hidden Markov models, the hidden Markov model had a transition model and a measurement model, right? These were probability distributions. Similarly, here, this optimal sequence of actions in a stochastic world is going to be the result of us solving the MDP, solving, in other words, for the sequence of actions. So the solution will come at the end, but before the solution, we need to understand what models now we have to assume, right? So notice that we are still in the Markovian space, right? So there must be some models around. So after we define the models and understand them, then we can sort of start understanding the objective of the agent. So we need to understand, to solve an optimization problem, we need to have an objective function. So we need to define the objective function. And then after we design the objective function, we need to see the problem, how it evolves, and decide on what kind of algorithm could potentially solve it. And this algorithm will result into, now I need to go forward, and I need to go there, and so on. So if my problem here is to exit the room, out of the possible many actions that I can take, right, there must be an optimal, and I'm here, must be an optimal set of actions that will maximize an objective. Let's say the shortest path to exit the room. Other actions I can take, and I can go and exit the room from a million different possible actions, will not be optimal, but one of them will be, and that's what we are trying to find. Now, similar to what we have done in the hidden Markov model problem, we will need to define a probabilistic graphical model that will govern the conditional distributions that we are having here, right? So there are some distributions because obviously there are some random variables. So I'm going to draw it over here. So A. I hope you remember what these arrows mean. What do they mean? What the arrows mean? In hidden Markov model, what was the meaning of an arrow? From one variable to another. In the probabilistic graphical model, there was conditional dependence, right? This was dependence. There was some probabilistic dependency that I'm drawing right now. Okay? So and also I'm making a convention. Convention I'm making is that R, also I made a convention in HMM to make the analogies. First I'm taking action and then I'm going to get a measurement. I told you at the time. So here we're saying R and S prime are determined at the same time. when we execute the step function with arguments S, 8. So I'm making an action from state S, and I immediately transition to S prime and receiving a reward down. So this PGM will define now, definitely defines a conditional probability distribution that I can call P model, but I'll drop that model for clarity. So I'll call this, who can tell me what this diagram defines? What distribution? P of what? P of S prime. Where can I be and what reward I will receive? Condition that on S, comma. This is called MDP dynamics. The literature, MDP dynamics. Out of this conditional, I am going to start now defining with some well-known to us now operations, the equivalent measurement and transition model that I was telling you in the HMM out of this. Okay, so I am going to define the transition model. Which is going to be P of S prime. What rule is this? The sum rule. Marginalizing out the reward. You probably remember this. It's exactly the same. Also, what is the problem? Distribution of rewards. Marginalizing of the S prime, the MDP dynamics. So let's now use this as just definitions, just to see an example of a transition model from a simple MDP problem, which will involve a grid world, very small grid world. Also, your textbook has that kind of example, so I will stick to it. The grid world is as follows. Okay, so I will explain now a little bit about the transition model. Although it's kind of old news for us, but nevertheless, we said we're going to go slow. So this model has 4 columns and 3 rows. Okay, this block, this cell cannot be occupied. There is 1, 2, 3, 4, 1, 2, 3. And every single cell I have gone and assigned to it a reward value. Every time that I'm going into this kind of cell, I'm going to pick up a reward, minus 0.04. I'm not going to write all the reward values, but you can imagine this number across the whole space, except from this cell over here and this cell over there, which is the equivalent to the pit. You get a large negative reward when you go there, and you get a large positive reward when you go to 4,3. So the environment is stochastic in a sense that I may be going into the intended state with probability 0.8, but I'll be able to also I will go sideways with probability 0.1. So the agent will start from an initial kind of cell, let's say 1,1, and wants to move optimally in this environment. When I say optimally, we'll define what optimal is, but for now, we just want to understand the transition model, okay? So the discussion is kind of limited here. So what would you write with respect to the transition model? Okay? How would you specify it? You probably specified it as a set of matrices. What is the first matrix? Well, let's fix an action. And if the action is up, let's say, so I'm going to do only one. So for every single, you can see the elements of the transition model, right? So it's given S comma A. So I'm fixing the A, right? And also I'm fixing the S, right? And then you need to write something about the S prime, probabilistically something, right? So if this axis is the S prime axis, right? And this axis is the S axis, how many states I have in the problem? Have 11 possible states. So it's no surprise that I will be able to write, let me write a few of them, and so on, right? I can write over here columns. There will be far more than what I'm drawing right now. But let's assume that this is S11. What should I write in the S11? The first cell, what should I write? The agent, okay, I forgot to tell you about the action, going north. The first cell will be, I'll give you the first one, 0.1. Second cell, 0.8. Third cell, 0. Fourth, 1, 0.1. The rest will be zeros, right? So the summation of this guy will be 1. But that's what we can do. We can actually start calculating for every possible starting state, S, all possible probabilities of going into any other S prime state if we take an action of up. We will do the same for down. We'll do the same for right, and we'll do the same for left. So we have fixed all 4 possible actions. For all possible actions, I have now a transition probability tabulated in the table. Any questions on this? So I'm just looking at my transition model that someone gave me, the behavior that someone imposed on me, the stochastic transition model, and I'm just tabulating it. Why am I tabulating it? Because I will be using it to make calculations. Okay, I'm not just tabulating for the benefit of tabulation. Hopefully you understand that. So, any questions on the transition model? I think it's pretty straightforward. We have done this before, in fact. So let's look a little bit at what we'll call now the reward function, because this is where things are becoming a little bit complicated. So reward function. I will define the reward function as reward functions will come into two versions. One is a reward of S comma A. And basically we'll say that this function will say, okay, I don't really mind where you will end up. Right? The moment you take an action from state X, I'm going to send this. And the other form will include the S prime. So this will be an expectation of RT, or RT again, capital is a random variable according to Saturn's terminology. ST minus 1 is equal to S, AT minus 1 is equal to A. Expectation. It is really the expected reward received after we execute action A from state S. And I think it's worthwhile decomposing this expectation. Now, decomposing in a sense, replacing this expectation with some kind of a summation, because it will reveal certain things for us, which is present in MDP kind of problems. So can I write the following? Can I write the following as summation over R of R what is the definition of expectation? I'll open a box here, right? Definition of expectation. Expectation of X, right, is equal to summation of X, P of X, right? Or in the graph. But summation is because we are, let's assume that we have this kind of discrete random variable here. X times P of X. So it's summation of R times P of R. How do I extract the P of R? I can simply extract the P of R by marginalizing over S prime of the MDP dynamics, S prime, comma, R of S, comma, A. That is P of R given S, comma, A. Pure definition. That is the definition of the reward function. For every single state that I am starting the interaction, or I am right now, and taking an action up, down, left, and right, I will have a value, right, that it will represent this. Okay. Now, the second form, I told you there's going to be a second form. It's R of S, comma, A, comma, S prime. Well, the definition is almost identical to the previous one, except that now I'm conditioning also on the S prime. I'm not going to write the expansion to that. It's okay. I'm not going to write it, although it's kind of trivial to write it, exactly the same kind of formula, more or less. But what I'm going to suggest here is gradually with this kind of reward functions, and it's a function of this kind of arguments, right, of the environment, right? The transitions of the environment is giving me also the actions I can take. I need to start approaching the definition of the objective. So that's basically the agent will have some behavior that it will obviously tries to maximize something. Well, if for every good interaction I'm executing, I'm receiving a positive, let's say, reward, I will try to maximize the summation of all the positive rewards that I will receive throughout the interaction with the environment. I think that's intuitive to assume so. Okay, so let me write it down. The goal of the agent is to maximize the total amount of reward it receives. And we will somehow need to put this in some kind of an equation. So we'll define now a new random variable called the return to lump together this summation of all these rewards, right? But we will use the discount factor in that equation. So I'll show you now how this return, I will symbolize it with capital GT, and it's going to be RT plus 1 plus gamma RT plus 2 plus gamma squared RT plus 3 plus dot 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 is equal to summation from small letter k is equal to 0 to infinity, gamma to the power of k, r k t plus k plus 1. So if I'm here in this kind of state, I have a range of actions that I can take. Obviously, across this, all possible actions I can take, but also across all possible future states that I will be able to reach by taking these kind of actions, right? There is a probability distribution of rewards associated with it, right? So basically, the return says, okay, if you execute this action, you will get an immediate reward, whatever the immediate reward is, right? The reward function will send it to you. From that state that you are in, this S prime, you will get another action, you will get another set of possible rewards into the future. And so on and so on, you'll do exactly the same thing. And the question becomes, what role this gamma plays? Gamma is a discount factor. It's like almost like the net present value of what I got right now, right? Like money. I think about it like money. So if gamma is equal to 0, what this sum becomes? The immediate reward. I don't really care about the future reward. It's very myopic to today. You know, obviously the $1 million is worth much more today than it will be worth, 10 years into the future, right? So all I care is I'm effectively going to incentivize the agent to just maximize the immediate reward. The agent doesn't really care about the future. Okay? Greedy, pure greediness for the present. If the gamma becomes, let me write it down, if gamma is equal to 0, then GT becomes RT plus 1. If gamma approaches 1, what happens? GT is going to be, these terms are going to matter far more than if gamma approaches 0, right? So these are the two things that are happening. The gamma is hardly 0, but gamma is either going to be some number between 0 and 1. So if gamma is approaching 1, then the return, the agent is, the return is such that incentivizes the agent to think long term. And if gamma is close to 0, short term, okay, but not entirely just pure for now. So I hope this is kind of intuitive. Now you're going to say, hold on a second, why this kind of infinity here? So this, don't be confused by two things. One is like this infinity, this interaction may last forever. For example, in this problem I just gave you in this kind of grid wall, the agent may decide to move forever here. may decide to do that. So it will move forever. Will never interact. Will never terminate. Now, this is what I'm trying to introduce now is the difference between this, the lack of termination, right, and the deadline. Yes. So, for example, many agents will have quite different behavior if there are deadlines. Okay? So, for example, think about your what assignment do you have? The basketball assignment? No, you don't have the basketball assignment. Let's think about basketball, right? So the teams have certain strategies, therefore adopt certain policies up until 10 seconds before the game ends. What do you see the players do in the last 10 seconds before the game ends? They start throwing the ball, from the end of the court to get into a lucky kind of 3 points or whatever. So the strategy changes completely. When there's the deadline, the strategies are typically quite different than when there isn't. So we will call these problems infinite horizon problems. Our problem setting is easier than the finite horizon problem where there are deadlines. So this is basically no deadlines. So we get a return. Mind you, this return is not something deterministic, it's a random variable. Because it's a summation of this random variable. So for every experience until I terminate, the fact I terminate does not make the problem finite horizon. Hope you recognize that. I just terminated, just exited the room. The interaction cannot have finished. So hopefully everything is kind of despite the I will call it assignments here with expectations. I think at the end of the day we see problems that this at the end of the day is a lookup table. It's a lookup table. It's just like the precision model, it was a lookup table. This guy is also a lookup table. We will need to come up with a reward function, whatever that is. And I hope also that the return is also kind of intuitive. We are going to get some probability distribution of returns, no matter what we do. Yes.
Yeah. In contrast to like the infinite horizon, can we whip each rollout with like a fixed episode time length, like capital T?
In some problems, yes, it is possible, right? But not in all problems, right? Because at the end of the day, the trajectory will terminate. Now, if you fix the trajectory because you have some other considerations, maybe compute or approximations to some values, functions, and things like that, right? That may come as a discussion in reinforcement learning. This can be done also. But right now, let's leave it like this as a general kind of definition of a return. And let's now move on to the last definition of the day, which is called a policy. So what is a policy? So as you can see, everything we've done from the beginning to now is just definitions. There's nothing else. There's no algorithm, there is nothing, just definitions. So the definitions will continue into the next lecture with the objective function. So starting from the next lecture, I will define the objective function. But for now, I'm going to stop here. It's called the policy. Policy, and I'll symbolize it with pi. And I'll define the policy as a mapping from state to action. And I'll have policies that are stochastic. And therefore, I will write it as pi of A given S, which is effectively a probability distribution. P of A0 given S, comma, P of A1 given S, comma, dot, 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 P of A cardinality set of the set of actions A given S. So I will execute, if I am in S, I will execute an action with some probability. So I can go here with probability 1/4. I can go here with another 1/4. Over here another 1/4. Backwards with another 1/4. That's like a uniformly random policy. Is this policies, stochastic policies, why you're doing that? Why you not always go towards the door? Because in most problems, I don't see the door. That's the simplest answer. I have to explore the environment, hit states that I do not know any rewards right now. I'm myopic in this respect, right? And as I gain experience, I will be, of course, understand a little bit about the environment interaction and try to move into better and better states. A subset of stochastic policy. So over here you will see 1/4, 1/4, 1/4 for this specific 4 actions, if I got 4 actions. A subset of these, a special case of stochastic policy, is a deterministic policy. From this state, I will go there with a probability of 1. That's a set action that I have taken. I have to predetermine. With probability 1, I'll just do that. Whether I will reach my intended state or not, that's not my job. Right? This is the job of the transition model. The environment will tell me what S prime I reached. But I can have a deterministic policy to always do that. So this is the other extreme of deterministic policy, where effectively a good action influence. So I'm going to stop here tonight because if I go in now into the objective functions, then I need to define. I don't want to interrupt it for 5 minutes. Okay, so I'll give you 5 minutes back. Yes, go ahead though. Yes.
So we would want a stochastic policy for POMD, like partial observable MDPs, right? Is what you said.
No. Partial observable MDPs is a different thing. For example, right now we have a full observed kind of MDP, but still my policy can be stochastic. Because I need to explore all states, right? So I cannot, in other words, in many instances, despite the fact that I have not really I can expand my tree. We'll see that the next time. I can expand a tree, if you like, of all the possibilities, and I can then, because I know all the probability kind of distributions, I can understand the value of being here. So next time we need to quantify what is the value of being here versus the value of being over there, or versus the value of being at the end of the room. There are 3 different values. Those values entail expectations, no matter what. Fully observed, partially observed, entail expectations. Yeah, so that is for today, and I hope it wasn't too painful, but it will become more painful next time for sure. Okay, yeah. We'll see how that goes anyway. Okay.